more and more, it looks like more and more people are coming. Okay. Maybe meanwhile people still come, I can share with you the, let's see. I share with you the correction of yesterday's tutorial. Let's see. Okay. Okay, so here you should find the answers for yesterday, yesterday tutorial day 1. So yeah, if you had still blanks from yesterday, and if you want to look at it during the lunch break, there you can. Okay. Mm-hmm. Okay, so I guess we can start for today. So good morning, everyone. Thank you for joining again today. So for the second day of the workshop, during the morning session, we'll focus on the theory, or introducing a new model, a new kind of model, which is a multi-layer perceptron, which is a kind of neural network. And so I'll present that in the first session today, first part of the morning session, and then Ronald will talk to you about model evaluation and challenges of artificial intelligence in healthcare. And for this afternoon, we'll proceed with the tutorial we started yesterday and try to implement multi-layer perceptron, as well as doing a bit more model evaluation and fine-tuning. Okay. So for those of you who just joined, I shared in the chat a link to the tutorial of yesterday, day 1, with answers, in case you didn't have time to fill all the blanks. So before starting to talk about neural network kind of models, I wanted to do some recap of yesterday. Let's do a quick recap about the machine learning classification setup. So as you may remember, yesterday we always start with some data. We have a good training set, which is composed of both X-train, which is a table, an observation table of different samples, like different patients, for instance, described by a range of features: heart rate, temperature, medication taken, etc. And those samples, also we have Y-train for those samples, which is an observation target output variable that we would like to predict, Y-train. And here in this workshop, we focus on binary classification problems. So the label is with 2 classes, either 0 and 1, like ill or sick or healthy, survived or didn't survive, etc. This kind of problem. And in machine learning, so what we're interested in, so here I take again the example of logistic regression model. So we have some shape of a model that we know we would like to use to answer this question, to predict this target output variable y. So we have a shape of a model with some parameters that depend on some parameters, W and B, so weight and bias here, that we would like to fit to the data. We need to estimate. So to do that, we need to train our model using our training data set in order to estimate the good W and B parameters. To do so, it's not always possible to get a closed form solution for the best parameters W and beta and B. So what we need to do, for instance, for logistic regression, is to define a metric that will measure the error. So how far the prediction y hat will be from the ground truth y. So here, let's recall that yesterday we introduced the cross-entropy loss function, and we will need an optimization algorithm. So yesterday we focused on gradient descent algorithm in order to iteratively update the parameters W and B in order to iteratively update the parameters W and B so that depending on the training data set in order to minimize the metric that we defined. Okay, so that's an overview of a machine learning classification setup that we saw yesterday. And yesterday we also focused on three main types, three different classification models in binary classification: logistic regression, supervector machines, and k-nearest neighbors. It's three examples among a wide range of other possible models, right? So logistic regression, so here I just put the table of the pros and cons of each models, as well as an illustrative figure to represent how those discriminative classifiers work. So the model is the line in black that try to discriminate between the two classes. And for k-nearest neighbors, it's a non-parametric type of model where we just look at the neighbor points in order to attribute a class. Okay, so each model has its pros and cons. Logistic regression is quite simple to interpret, to deploy. It works in many cases. But it will require feature engineering usually to be efficient. Supervector machine used to be state of the art. It was very well studied, and it will allow you to handle nonlinear data, nonlinearly separable data when you use kernel. But it's quite hard usually to find a good kernel, and it's also slow to train and sensitive to outliers. It relies on actually one data point to draw the boundary, the margin and the vector, the decision boundary vector. And k-nearest neighbor is quite intuitive to understand. So that's an advantage. It's also quite simple to deploy, but one main drawback is that it will require to have your data set when you share your model. You need to share the data set with the model, right? And it's sensitive to normalization because you use metrics like distance or similarity metrics to measure how close the points are from your new test sample. So you need basically the features to get the same weight. So you need to you need to find a good normalization. Okay, so that's what we a summary of what we saw yesterday in terms of models. Do you have any questions so far from yesterday? Okay. So for the rest, do not hesitate as well to interrupt me during when I talk. Okay. And so today, what we'll focus on is a new type of a new classification model, which is a type of neural networks. So neural networks is a wide range of different models. So I'll do a quick introduction about that. Then I'll focus on the multi-layer perceptron that is can be quite useful in our type of data set that we saw in the tutorial. And after that, I will introduce other type of architectures that are usually more suited to other kind of input data. Okay. So first about neural network, let's talk about the inspiration behind it. So neural network, or artificial neural networks actually take the inspiration from the brain and from neuroscience with all the neurons and connections. Because it's sometimes possible to model the brain neurons by some function that takes some input signal, compute some function inside the nucleus, and then release some output signal that will be transmitted through the axons to other neurons, to other cells, right? So that's the inspiration behind it. However, I mean, the inspiration it stops here, and it gave the name to the artificial neural network. But behind that, it's not really close to how the brain functions, right? It's just a very simple model of the neuron. And there are some historic milestones that maybe I would like to share, just maybe to show you, to give you a sense that neural networks, even though it may seem quite recent, because it has been very fashionable, it has become very fashionable only in the past 10 years. The concept is actually quite old. Because perceptron, for instance, was introduced in 1957, so it's quite old. However, the good performances started to arrive more recently. Once, for instance, the backpropagation was established, or also once the computing resources also increased, right? But the concept is quite old. Then I would like to introduce the slight difference shift between machine learning and deep learning. So deep learning is a subtype of machine learning, okay? Conceptually, it's very close. It's just that in traditional machine learning, what you'll do is, like, for instance, if you have some input, like here, an input image, you will manually take extract some feature, right? Oh, sorry. You will have to manually extract some features in order to fit them, to provide those features to a trainable classifier like SVM, logistic regression, etc., in order to predict your output variable. So in SVM, but we have a lot of normally we didn't do it really in the tutorial, but normally keep in mind that you need to spend a lot of time on feature engineering, right? For SVM, you need to make sure you filtered for outliers. For k-nearest neighbors, you need to find good normalization of features or good combination of features so that they have similar weights. In deep learning, the idea is that you have much more data, okay? You have much more data, training data. So instead of having, like, for instance, 1,000 samples, like it's like the range that we have in the tutorial. Let's say you have more like 1 million samples. So you have much more data, and then that's why you switch from machine learning to deep learning models that have much more parameters. And then you can expect those deep learning models to do some feature engineering for you. So the idea is that it will extract different kind of features, low level features, mid-level features, high-level features, etc. And those features would then be given to the classifier. Okay. Okay. It's just so it can do some more feature engineering more than traditional machine learning, right? But there is a lot of assumptions sometimes when you read articles or more like blogs online, where it says that deep learning does not require any pre-processing because it does everything end to end. I would, I think it's not necessarily true because most of the time, especially in healthcare, you don't have enough data to just feed everything to the raw data to your deep learning model and then expect your model to learn exactly what you want. So in practice, I would just say that it will require also at least some feature engineering, and you can help your deep learning model learning faster by doing good feature engineering. However, what a deep learning model may be able to do, and maybe not a machine learning model, is to learn maybe higher level features. So a more complex combination of the features that you give, right? Okay. Now, another idea that we can raise, because deep learning, as you see, deep learning model is not a recent concept. So why do we see so many like deep learning papers today? Why do we hear always about deep learning everywhere? Basically, one of the reasons is that hardware have evolved. So now hardware can provide faster computations thanks to GPUs, graphic power units. And as you can see on this chart, this timeline, so you have some GPU models from like NVIDIA and Intel, which are the bigger competitors in terms of GPUs. So you can see that the performance measured in giga floating point operation per second. So this performances has increased dramatically over the past decade, right? And so it has enabled a lot of model training that were not possible 50 years ago, right? And those graphic power units are quite interesting in terms of performance because they are built for high compute density and for parallel operation. okay? Also, what has changed in the past few decades is that there are much more data sets available, publicly available data set like MNIST, which is a hand-digit data set. Okay, so a data set with a lot of 1, 0, 3 handwritten. ImageNet, which I think has around like 1,000 different class of like cat, dogs, fruit, vegetables, animals, etc. With millions of instances. So this is publicly available now. You also have software libraries, open source software libraries, mainly built in Python, that makes with a good documentation that makes it easier for a researcher or even for industries to implement some models. And you have a large scientific community now with a strong expertise so that contributes to data to deep learning model deployment. Okay. So now about the deep learning theory. So here I just wanted to point out that actually deep learning theory is a whole research field, because there are a lot of unknowns when we study deep learning models. We don't necessarily fully understand why it works so well, basically. So it's super popular because it can solve a lot of problems that were not possible to be solved before. But there are a lot of unknowns still. So first, you may see also out there when you read, sometimes people speak about the free lunch theorem, no free lunch theorem. So this expression, this phrase means that there is no universal learning algorithm that could be trained and that could solve all problems, all data sets, all research questions, right? So the idea is that deep learning models need to be adapted to the kind of research question you want to answer. Okay. Then then about generalization. So one thing that is very one thing that is very special about deep learning model is that it is able to generalize very, very well, even though there is many parameters involved, right? So here I did some illustrations, try to give you a sense to what it what it means. Okay. So first here on the left, if we see like a linear regression or a linear supervector machine, okay, you have only like 2 parameters, for instance. So it's only a line. Then let's say you use SVM with a polynomial kernel of order 9. So you use a high order polynomial function. Then you are able to draw a boundary that is not linear and that is maybe possible to encounter for a more complex data set. Okay. Okay. Now let's imagine that you take much more parameters than data points. Okay. Which is what we observe in deep learning. There are deep learning models with a huge amount of parameters, sometimes more than the number of training data points that you have. Then you may expect, I don't know, a boundary decision, very, very tricky boundary decision like this that actually overfits, right? Because it almost tries to draw a circle around every data point. Because you have so many parameters, you can really modify the decision boundary in order to encompass all the data points. Okay. But what is observed in deep learning models is that when we take even more parameters than this case, we don't really know how, but it has good generalization property. It's able to draw a line, not necessarily linear, but that will be able to generalize well and not draw a circle around every data point. And this behavior is not super well understood. So here, what I just described is illustrated in this chart. So let's say that the risk is like the error, okay? The error of prediction. Here you have a training error, and here you have a test error. The complexity of H, which is your model, is the number of parameters of your deep learning model. We see that when we increase the number of parameters, first we don't have enough parameters, so we kind of underfit. Then we have too many parameters, okay? So we fit very well the training data sets, but not well the testing data sets. But then what we can observe in practice, and that is quite surprising, is that when we increase again the number of parameters, then we manage to have some better generalization than before, right? That's quite surprising. Okay. Now about deep learning in healthcare. So one I guess main milestone in the deep learning for healthcare is a paper published in Nature in 2017, so quite some time now, that used deep learning models, convolutional neural networks, more precisely, to detect skin cancer, to be able to distinguish between benign and malignant skin dots, okay? And even to classify between different kinds of skin dots, skin beauty points, okay? And so that was the research question they wanted to answer. So to do that, basically, they use as entry input skin lesion image. They use some deep learning network using convolutional neural network. And that you see, it's not binary classification here because they really have a lot of different classes. And then they also try to predict a risk of benign, whether it's benign or malignant, right? Okay, and what is interesting and what was really one major milestone here with this paper is that they achieved to have better or comparable accuracy with compared to dermatologists. So they asked several dermatologists to do to manually classify each image, thanks to their expertise. And then they compare it with the performance of their model. So remember here it's a confusion matrix, but here it's not binary, it's multi-class. So basically, if you have perfect classification, all the predicted label will be equal to the true label. So all the diagonal will be very dark, and the rest should be white. Okay. So what you see here, I mean, just visualize, but you can look at this paper more in details, is that their model has a better average, better performance than an average dermatologist. So here's 2 dermatologists, let's try with some more, okay? So it was the first achievement because it was the first time like that deep learning model could reach reach a medical doctor performance for one specific task, okay? Okay. Okay, so now that we have some insight of deep learning field, subfield, let's talk more details about a specific kind of neural network, which is multi-layer perceptron model, okay? Okay, so first here, I wanted to give you a general idea of multi-layer perceptron. Which is to build a complex classifier from more simpler building blocks. So it's a bit the analogy with the brain still functions here. Basically, you have you can think of a multi-layer perceptron as a set of neurons, set of small functions that are combined together, where you have some inputs, and then they give you each neuron give you some output of their own function. Then you combine those functions together, okay? So there are some websites out there. So I don't know if I can share it. Can you still see my screen? Yes?
Yes, yes.
So you have here's some link to now there are some very good websites out there where you can try to look at to visualize how things work when you combine different neurons, different artificial neurons together. What will give you what the output will be, what happens when you increase the number of artificial neurons you combine together, etc. So just I put you some links here you can play with, okay? Okay. But the idea is really to combine some simpler building blocks, okay? So in order to introduce you multi-layer perceptron, I would like to use what we saw yesterday about logistic regression. Just the idea here is to view logistic regression in a different way, to view it as a building block for multi-layer perceptron, okay? So let's look at what we saw yesterday and let's decompose the logistic regression model into a computational graph, okay? So here you have, as input, you have 3 main things. X, which would be like your sample feature, okay? W, the weight, and B, the bias. First, you can do some scalar product on X, on your feature. So you weight your feature by some weight, W. Then here you add the bias. Then here you apply the sigmoid function. Remember the sigmoid function that squashes our real number into, that turn the real number z into a probability. Okay, so you have this probability y hat. And from y hat, you can then compare it with the ground truth y during training and compute the loss, compute your metric. So this is called like forward pass from input to output to loss computation. Then now we'll we can see like training and gradient updating, parameter optimization as some backward pass. Let's talk about the backward pass. So you have a loss here. So let's recall that yesterday we focused on the cross entropy loss function, which is negative likelihood loss function. So negative likelihood here for one sample. Let's note that in the binary case, so this conditional likelihood follows a binary distribution, okay? And if we if we replace y hat by the expression of the logistic regression is replaced here. So if it follows binary distribution, then we can compute the negative log likelihood. We can express it here, right? Okay. Then the idea is to go backward, okay, in order to adapt the model parameters W and B. So to do so, we need to take the derivative of the loss function. So we derivate, here we will derivate the loss function depending on y hat, okay? So if you compute it, it's a partial derivative because you're supposed to only y hat varies, okay? So if you calculate it, you will realize that it will be in this form, right? So you have to compute the derivative of the logarithm here. Then if you go backward one more step, okay, here you want to compute the derivative of a cost function depending on z. And here you use some trick, which is called chain rule. So basically you can say that derivative of j depending with respect to z corresponds to the derivative of j with respect to y hat multiplied by the derivative of y hat with respect to z, okay? So it's a bit like you could simplify the derivative of y hat. And here we'll use the advantage of that the sigmoid has a very simple derivative. So we can easily compute this number, right? This derivative. And doing backwards like this, you'll be able to calculate gradients and then update your weights. Okay, it's just another way to view what we saw yesterday. So we continue, and then you can, if you continue one more step, you will have a derivative of a cost function depending on the two parameters W and B you're interested in. And then you can use those approximations of the derivative to update your weights and to optimize, to minimize the cost function and find good, good estimate of W and B. This process of going backward to step-by-step compute derivative using chain rule is called back propagation. And it's a major step, major idea, major principle in neural networks that will enable us to train neural networks. Okay. Okay. And now, so if we do some summary, we see that we can rephrase like the logistic regression model we saw yesterday as a computational graph. Now, we can go one step further and rephrase it. Okay, rephrase this this computational graph like this on the right with neurons. So it's very similar. It's just like here you have X, okay, and you between this neuron and this neuron you will apply some affine, so linear function W and B, and you will also then apply some the sigmoid function and get the output. So Z then will be the combination of will be the scalar product of W and X. So if you have X1, X2, X3, which is the different features, stands for the different features of your input example. So you have one weight for one feature, okay? And you combine it together. And this creates like layers, neurons, and layers of neurons. And the idea here is that you have this relationship where for one layer, like the layers, the output layer Z, is computes a function that is extracted from the previous layer in green. Okay, so this is like, I guess, the simplest neural network that you could think of. Now, the idea in deep learning using multiple perceptron model is to use this this very small neural network that we just saw as a building block, and to increase the number of layers. So by adding, for instance, hidden layers. So previously we had only some input and directly the output. But here we can think of intermediate neurons, intermediate functions, or intermediate building block, okay? And each building block will have its own weights and bias, okay? As you can see here, H1, it's also like, for instance, a sigmoid function. It's also like same expression as the logistic regression, but we'll have so its own weight and B that will have to be estimated. And so, the sigmoid function so is called the activation function. The idea here is to compute many linear functions, but adding to each small linear functions some activation nonlinear function in order to enable the model to classify or to create some nonlinear relationship between features. Okay. So I would hope here that you get a sense that using those kind of neural networks of multi-layer perceptron, that you will be able maybe to solve a nonlinear problem where data is non-linearly separable, because you can really do some nonlinear combination of features thanks to the activation functions. So the model that we can see here is said to be fully connected. Why? Because the number of weights is equal to the number of inputs by the number of outputs. And the number of bias terms is the number of outputs. So it means basically in fully connected layers that each node is connected to all nodes of the previous layer, right? You could think of like not fully connected models where, for instance, X1 will be connected only to H1, for instance. And maybe X2 will be connected to both H1 and H2. Here it's fully connected, so each node is connected to all nodes to the previous and next layer. Then about activation functions. So for now, I stuck with sigmoid activation function because it's the one we saw with logistic regression. And it was, I guess, one of the, initially one of the most used activation function. However, now in neural network training, there are a lot of different nonlinear activation functions that you can use. And like hyperbolic tangent, 10H, rectified linear units. So you see it's not linear because you have here, and it's not actually, you cannot derivate here. So it's linear only for positive values. Or parametric rectified linear unit. So here you can put some negative instead of putting everything negative to 0, you can put some negative value. So you can change it. It's like a parameter you can change. A few years ago, I mean, at least a few years ago, rectified linear unit was super popular for neural network training. And yeah, and now there are some more complex activation functions that use also like some randomness that you can use. I didn't put all details here, but basically it's something you can really change. The idea is for activation functions is really to add nonlinear possibilities to your model. Okay, and now I would like to introduce you to some elements that you will come across if you implement or use for your research or project some neural networks that are important to improve training. Basically, so first thing that maybe you should be aware of is that the initialization is very important, because so it's like logistic regression we saw yesterday. When you have your multi-layer perceptron, so with all the neurons and each function has its own weight and bias term. First, you don't know what a good estimate of those parameters are, and you have much more parameters to estimate compared to logistic regression. So what you do is you randomly initialize the parameter. Then you do the forward pass and backward pass that we saw in order to compute the gradient and then optimize, update the weights. However, but sometimes it's quite popular to use, so I don't know how to pronounce it, sorry, Xavier initialization, in order to basically to have some upper bound and lower bound of to have some upper bound and lower bound of what your output could be. Because basically, if you randomly initialize all your parameters, let's assume that then it can happen that your y hat predicted output will be super high, for instance, will like almost explode. And maybe you don't want to get that, or you want to control that at initialization. So you can use Xavier initialization to do that. It can be quite important, especially for small data sets. Then what you can have also to improve training, so we introduced that yesterday already, is the adaptative learning rate. So here, like you have your gradient to minimize, and you have a lot of parameters to estimate. So maybe you may want to have, as I introduced yesterday, to have some high learning rate at the beginning of your training, and then reduce the steps in order to have a higher chance to converge to a minimum of your const function. Okay, so like quite a lot of methods out there or algorithm to adapt the learning rate during training. It's a whole field also. It's a whole research field. Okay, another element to improve training is adding batch normalization. So we introduced also yesterday the idea of batch training. When you have a big data set, maybe you don't want to compute the cost function after iterating over all your training samples, because if you have 1 million, it can be very long, right? So maybe you want to select some small batch and to iterate, so to calculate the cost function after each batch, which is more reasonable. So something that is quite recent and can be quite interesting to decrease the training time is to do batch normalization. So the idea is that for each batch, so here you have a batch of M samples, right, described by several features. For each batch, you want first to standardize your item depending on the mean and standard deviation of your feature. But then what batch normalization algorithm does is that it adds also two other parameters. Two other parameters, gamma and beta, that are learnable, that will be learned during training. Okay. And we don't really understand, at least I don't really understand why it works, but it's quite popular to use that in order to decrease training time without affecting the accuracy. Okay. Then to improve training, so you can also add regularization, like for logistic regression that we introduced yesterday, L1 or 2 regularization. It's quite popular, especially here because you have so many parameters. Maybe you may want to reduce the number of parameters, or at least to penalize a higher number of parameters. So it has to be to really improve your model to add more parameters. Then another element you can use is to add dropout layers. So here's also an architecture of a multi-layer perceptron, fully connected. As you can see, each neuron, each small building block function will be linked to all previous neurons in the previous layer. What you can add is dropout layer, where basically you will randomly turn off some neurons during training, okay? With some probability, so usually 0.5 is taken. And it's actually equivalent to doing some online regularization. So that's something that's quite common to add to your model. And another thing that you can use during training is early stopping. So the idea when you train a multi-layer perceptron or a neural network, so you have some libraries where you can really monitor the error. So you can really see like what is the error depending on how many epochs or how many iterations on your data sets you have. So you really want to monitor that to ensure that your training error and your validation error are both decreasing. What happens very often is that first, so your training error is normally always decreasing as you compute your gradient, etc., you update your parameters in order to really decrease this error. But the validation error, usually what it does, this is quite like common trend, is that first it will follow the training error and decrease, but after a while, it will start increasing again. That means here that you are starting overfitting. So you overfit on your training data, but you're not able to generalize well on your training data. So then you can add some early stopping technique to your training in order to stop training, for instance, just when the validation error starts increasing again. Maybe you want to stop there, to pursue training. That's a kind of popular technique. And another thing to improve training, to improve model performance is to, it's very popular, especially when you have images as input, is to induce invariance to your model with respect to some geometrical transformation. So for instance, imagine in your dataset, you have images of planes. And you want your model to be able to detect whether there is a plane or not. Basically, if you flip the image, it's still a plane, basically. It's still a possible image. I mean, you would like your model to be able to classify it as a plane, even though it has only seen plane going in this direction. So what you can do is to artificially increase your dataset by taking your original input samples, your original images, and maybe adding some transformation, flipping rotating, cropping, like maybe if it's a bit cropped, you may want your model to still be able to detect it. Color jittering, edge enhancements. Maybe the edge is a bit weird. The inside of the image is still there. Fancy principal component analysis, or you can add noise to your data, right? If the image is noisy or has a lower resolution, you may still want your model to be able to detect it, to classify it, right? So that's some techniques you can use in practice to make your model more robust. Maybe one last element is pruning. So this actually is not during training, but after training. So this is an overview of like your multi-layer perceptron, for instance, before pruning. So you see that each node is connected to every node of the previous layer. And you see that you can quite quickly end up with a model, a neural network, so multi-layer perceptron, that has a lot of parameters, okay? When you you add one hidden layer, you had, for one layer, you add some neurons, you can really easily increase your number of parameters. But maybe after training, you can maybe do some sensitivity analysis to check which weights, which nodes, which neurons, artificial neurons, are actually very important for your model. And by doing that, maybe you can see that, I don't know, maybe half of them are not very, very important. So you can remove them and then end up with a much sparser network that still have the same performance. Okay, so here's just a small summary of different elements that we saw to improve training of neural network. Okay. Okay, now neural networks, now what we saw, multi-layer perceptron. I would like to give you an overview of other types of architectures, even though we are not going to implement it or study it in this workshop, just that you are aware that other types of architectures exist. So it's quite a wide range, okay, of architectures. So you see there are, for instance, convolutional neural networks, or CNNs, that are well suited for images, autoencoders that are usually used for data reduction, compression, or denoising. Sequence models like LSTM, long short-term memory networks, usually for text, recurrent network, and generative adversarial networks. There are other types of networks, but there's like some of them. So first, maybe convolutional neural networks, because like it's quite popular, and those type of neural network is well suited for images. So if you work on medical images, for instance, you may want to use CNNs. The idea behind CNNs is that each unit is connected to a constant number of units in a local region of a previous layer. It's not fully connected anymore, okay? So here's fully connected case. Convolutional layer, each green neuron is connected to only a few previous neurons, okay? So the idea is that it's based on the idea that the spatial correlation is local in an image. So let's have another example with an image. So I don't know if you can see very well here, but it's an image of Albert Einstein. So basically, this is how the model, how you could represent passing this input image to a fully connected model. That each pixel will be like one, you have your 2D image, for instance, you would need to flatten it to create a single very, very long vector, one pixel with one value, grayscale value, and you will feed it to the fully connected network. The idea is that then it creates a lot of connections. And maybe you can think that this pixel out here maybe not very, not have any link, any connection with this pixel out there, right? Maybe it's not super relevant. What the convolutional layer will do instead is to take only a local information. Okay. And then why is it called convolutional neural networks? Because it's based on the mathematical convolution operation. So in 2D, here's just an animation to show you how it works. Basically, the idea is that your model will be some filter with some weights. Okay, so in orange here, you have you apply the filter, and so it's local, right? It's a small sub matrix within your full image, and then you actually apply this filter, this small window of weights, to parts of your image. Okay, and for each small window, you will get one convol feature. Okay, so it's just an overview of how it could be seen with more with not only like one single building block, but with like several, for instance, input channel. You have several filters that you pass. Okay. So here's like the filter matrix. You pass it to the input channel. You get a convol feature. Okay. And then so you can have it for the different input channels of your image. You can sum it. You can add a bias term. Okay. And then you can have an output feature, convol feature. Okay. And basically the idea is that this feature will actually result on what happens in a small window within your input image. Okay. So here's an example of a convolutional neural network architecture with a fully connected layers as in the end, in order to perform multi-level classification. So that's true that you can have several combinations also. You can, actually this was to show you that you could combine some convolutional layers, because first you may want, when you have, for instance, a hand digit like 2 here, you may want to extract features that are local because it's an image. So based on the local pattern, etc., if there is like straight lines, if there is like more like round shapes in your image, where is it located in your image? You may want to use convolutional layers to do that. Okay, but maybe in the end you will end up with some features that high-level features that are extracted from this image. But then in the end, the question you want to answer is it a 2, a 3, or 4, right? Which digit is it? So maybe after you reduce the number of, after you extracted high-level features, you may want to flatten your final, those features in the end, and then add some fully connected layers using multi-layer perceptron, as we saw before, in order to perform the multi-class classification. Okay. Okay. And then about convolutional neural network parameters and weights. So about those features, it has been shown basically that depending on how deep your convolutional neural network is, the first hidden layer will usually extract simple patterns within your image. So like horizontal lines, circles, vertical lines, diagonal lines, some patterns like that. But then deeper you go in your filters, in your layers, and the more complex the combinations can be. Okay, that may be possible then for a network to recognize a pattern like an eye or like some bird nose, stuff like that. Okay, and this is thanks to also the activation functions at each step of your layers that enable you to combine the different patterns, the different features in a nonlinear way, in a complex way. Okay. And so also, why are the patterns more and more complex the deeper you go? Also because basically, if you look at a CNN like field of view, you will see that basically in the first convolution, it focuses only on a few pixels in your input images, right? So from like if you have a small square within your picture, you cannot detect very, very complex pattern like an eye or a nose or a mouth, for instance. However, you can still detect wherever there is horizontal lines, vertical lines, for instance. So if you see that when you have some point in the convolution, it will result the field of view, the information that can be aggregated in this convoluted feature can come from a small field of view. But the deeper you go, then the more convoluted features you aggregated. And so then it means that you can actually aggregate information, high-level information from a larger field of view. That's the idea behind it. Okay. Now, autoencoders. So two main applications of autoencoders. First is data compression and using a latent representation, and data denoising using the reconstructed image. So here also I put some image example because it's quite visual. So the idea of autoencoder is to have this kind of shape of neural network. Basically, a neural network where you have an encoder. So you want the number of parameters, or the number of neurons to decrease in order to reduce the latent representation of your input image. And once you reach a bottleneck, then you can use a decoder to reconstruct the image. And so the idea of the autoencoder is to train the neural nets, this type of architecture, to reconstruct the image. So first, it will give you as output reconstructed image some very almost a noise. It will give you noise, very noisy image. But after updating the parameters, you can get closer and closer to the input image. And then what is interesting about autoencoders is that at some point it needs to reduce the information present in the input image, which means that if your image is quite noisy, in order to reconstruct it well, it will need to remove all the noise. So then you can use this trained architecture to denoise your new input images. Okay, or you can use this learned latent representation here in order to encode your input image into a smaller, into a much smaller shape. And then can help you sharing images that are too large without losing too much information. So just note that here on this example illustration, the neural network is fully connected, but you can use whatever you like. You can even use convolutional layers, then fully connected layers, and then again, convolutional and fully connected. It's up to you. It's just the general shape is really to have an encoder, bottleneck, decoder. Then sequence models. So sequence models are adapted to text input. So it's very popular in natural language processing, NLP. Let's note that a couple years ago, the gold standard for NLP, natural language processing, were hidden Markov models, HMMs. It was the most popular. However, now different type of architectures outperform those Markov models, such as long short-term memory network, recurrent neural networks, or transformers that use attention mechanisms. So I'm not going to go in details here, okay? It's not my field of expertise and we don't have enough time. But what you can remember, maybe, is that it's adapted to text input, and it allows, sequence model allows variable in input and output to have variable shape. So for instance, with convolutional neural network, you need to predefine the shape of your image, input and output. But here, when you want, for instance, to summarize a medical report or to translate from one language to another language, then you can expect like sentences to, you cannot predict in advance the length of your sentences. And maybe you want to give freedom to the model to, when you translate from one language to another, to use more words to describe this, the word. Maybe in English, you only need one word, and in French, you need 2 words. So you want to give this input-output shape freedom, okay? That's the idea. And then there's another type of network, so it's more for your general knowledge, which is called general adversarial networks, or GAN, adversarial networks, GANs. So the idea of those networks, it's a generative network. So that's quite kind of different, because most models we've seen so far is discriminative model, which means you want to draw a boundary between 2 classes. Here, you want to generate, to be able to understand what are the data and thus be able to generate them. The idea of generative adversarial networks is to use two competing neural networks that duel against each other. So you have a generator, that is a model that tries to draw samples from a training distribution, okay? For instance, it will try to generate realistic images of a tumor. And you have, on the contrary, the adversary or discriminator. So here you have like some noise. You have a generator, like from noise, it tries to draw a tumor image, okay? Then you have a discriminator model that is competing against the generator, because he is its role is to be able to distinguish between fake generated samples and real images of tumors. Okay. Is it a real image or a generator created image? Okay. And this is quite interesting when you want to try to generate new images for your data sets that are super good fidelity from your real world images, but different kind of tumors, for instance, that are not represented in your data set. However, in practice, it's super difficult to train, because you don't need to train one model, but you need to train two models, and they are in a relation. They have a relationship. They are competing against each other, and as you can maybe expect, first iterations, the generator will be super bad, because you feed it with noise, and you would like him to create a real looking image. So first iteration, it will look super bad. And the discriminator at the beginning, it will be super easy for him to discriminate between a real world image and a generated image. So you really need to find a good trade-off between the learning of the discriminator and generator, and super hard in practice. Okay. And maybe, so last thing I would like to talk to you about with neural networks, a challenge, I guess, a kind of a drawback that in for medical and data, healthcare data, it's a real problem. It's adversarial attacks. The idea behind it is that a lot of machine learning, deep learning models you will train will not be stable, not be robust. They have very good performance, maybe much better performance than other classical models or more simple statistics that you could use. However, they are not stable. So basically, one example, let's imagine you have a model that's like the Nature paper, that is able to distinguish between a benign and malignant beauty spot in the skin. So first you have a model that works well. But imagine you had to this image a very small amount of noise. Okay? So here's the image with the noise. Okay? We don't see any difference, but there is noise added to it. A very small amount of noise. The problem is that it may happen, and we see that in practice it can happen quite frequently, that then the model will recognize this new example as malignant. It will change the class just by adding some very small amount of noise, okay? Or a specific type of noise that is called adversarial noise. So specific noise, maybe sometimes you can just add one square, put one pixel at 0, and then it will change the class. So that's a huge problem, right? Especially in healthcare data, where we really need to be super confident about the output prediction. So it's really a big issue, and it can really be problematic if you develop, for instance, a model for healthcare applications that you would like to integrate to a medical device or a medical software, because to do so, you will need to get official approvals by, for instance, FDA, which is Food and Drug Administration, to be able to deploy your device in the US, or like in Europe, it's called European Medicine Agency, EMA. So you need to demonstrate that to what extent your model can work, and up to which noise it can still provide reliable predictions. It's really something you need to keep in mind, especially because of possible consequences in healthcare. Okay, and to end with, last thing for my presentation is deep learning in practice. Let's see that there are a lot of softwares. So for MLP, for the tutorial, I think we'll stick with scikit-learn because there is multi-layer perceptron in scikit-learn. But when you want to do more complex architectures, there are other softwares in Python. So it's libraries developed in Python, like Keras, TensorFlow, and PyTorch, that are also well documented for deep learning. Okay, and for hardware, so basically, depending on your data set, etc., you may, if you want to do for your research or your projects to implement some deep learning network, you may need to take into account the hardware equipment. Maybe only CPU will not be sufficient, or it will be way too slow for you to be able to train your models. Maybe you need to consider GPUs. So Colab also provides you some free GPU access, if I'm not mistaken. But it comes with some drawbacks of this Google shared tool. Okay, that's it for me. Any questions? No questions? Maybe if not, maybe we can do some break. I guess so. I guess I guess we can have a break and be back at 10:45 for Ronald presentation about model evaluation. Okay, all right. Okay, see you in a few minutes then.
Okay, so it's 10:45. Hope all of you are back now and we can continue. So, good morning, everyone. So, Hanae has introduced neural networks to you all. And now I'm going to talk about how to perform model evaluation and also some challenges and issues in applying AI in healthcare. Okay. So, clearly, just because we have done everything right and trained a model does not necessarily mean it is going to work, right? So when we define many of these concepts, we do so in a hypothetical or optimal situation. When we create a nicely labeled training dataset and then train our machine learning model, as you can probably expect, that does not always work out the way it is supposed to. So there are many issues that can come up. But first, we have to understand how to evaluate and test the models that we train. So now let's discuss about the evaluation process of supervised machine learning models, okay? But first, let's talk about the concept of overfitting and underfitting. So as we now know, machine learning models operate by, first of all, getting a rough set of weights which fit the training patterns in a general way, and then progressively learning towards a set of weights in the model for features that fit well the training data, right? But if learning goes too far down this path, one can reach a set of weights that perfectly fits the idiosyncrasies of the training data patterns so well that the model will only work well for the training data and not for the test or any other new data, okay? And at this point, we will have a low training error, but high validation or test errors. So if it is allowed to learn for too long, the model will become more prone to overfitting. And in order to get a good fit, we must stop at a point just before where the error on the validation or test sets starts increasing. And at this point, the model is said to have good skills on the training set, as well as on our unseen validation or test sets. So again, overfitting happens when the model fits to more than just the signals that is useful about the features in a dataset, and also begins to memorize the random fluctuations, anomalies, and noise that might be present in a training set. So that will harm the performance of the system on any new data. And another thing to keep in mind about overfitting relates to the choice of what kind of algorithm that will be used for our dataset or solution. So a very complex model, for example, like a very deep neural network that can accommodate high number of feature weights and that uses a high number of predictor variables, will frequently experience overfitting, especially in the case of small datasets. And as a result, these very complex models perform really well on training sets, but only because they have simply memorized the noise together with the signal in the training data. And then they do not really work well on any new data, okay? And now, if there is a term of overfitting, then we can correctly assume that there is also a term of underfitting. So a statistical model or machine learning algorithm suffers from underfitting when it is unable to adequately capture underlying structures in the data. So in other words, an underfit model is unable to obtain a good fit of the trends in the data. And we will be able to see this through poor performance on the training data. And as you can probably expect, an underfit model will also perform poorly on any new data, and it is overall undesirable. So most of the time, underfitting happens when the models or algorithms are too simple to fit more complex trends in the training data. And since the solution to this is relatively simple in most cases, which is to try a more complex model or algorithm, underfitting typically gets less time than overfitting in discussions about debugging. So appropriate fitting is the goal, right? And one of the major challenges that machine learning practitioners often spend a lot of time on in practice is how to tweak hyperparameters and algorithmic design choices in order to hit the sweet spot of appropriate fitting. So how do we go about achieving this balance about the opposing forces of overfitting and underfitting? So first, we need a tool to monitor the learning process. So specifically, we need a learning curve. So learning curves are one of the most common tools that machine learning practitioners use to monitor algorithms that learn incrementally from training data. And they are essentially plots of model performance over time as the model incrementally learns. And we can use learning curve to diagnose problems such as underfitting or overfitting, as well as the sanity check or debug our code and implementations. Okay. So in machine learning, since we typically use the concept of loss as an indication of how well a model is doing, so a common type of learning curve plot model loss over time, or as the model is exposed to more and more training data and validation or test data. And typically, the right combination of model architecture and hyperparameters will lead to large decreases in loss initially, which gets smaller over time as the model gets closer and closer to the optimal weights. But with some loss functions, we can never observe exactly zero loss, but usually a small loss, such as 1 close to 0, indicates that the training set was done close to perfect and few of any mistakes were made. And apart from the training data, we can also evaluate the plot and plot these for other validation or test sets that are not part of the training data as well. And we'll soon see that plotting both curves can be very useful for debugging. So let's start with underfitting. So the loss curve for an underfit model usually looks something like this, where both the training and the validation loss curve do not really decrease very much. And instead, they stay relatively flat at a high loss value. And this indicates that the model is unable to learn from the training set to reduce its loss. And even if you just see a flat training loss curve in general, without necessarily plotting the validation loss curve along with it, you can pretty much suspect underfitting is happening. And sometimes the curve may also show oscillating noisy values, but this will still be centered around a high loss value without significant trends of decrease. Okay. And now let's look at overfitting. So the loss curve for an overfit model usually looks something like this, and where the training loss continues to decrease over time, but the validation loss decreases to a point and all of a sudden flattens or even begin to increase again. So why is this happening? So if you think back to our discussion of overfitting, this behavior starts to make sense because the training loss curve is fitting extremely well to the training data, and so the loss is decreasing. But the generalization performance of that model on a validation set, which it has not seen before, starts to get worse. So basically, the model is learning to fit random fluctuations and noise in the training data, or memorizing the training data, and it continues to decrease the training data loss as we would expect. But this is happening at the expense of the validation loss when overfitting starts to flatten or become increasing again. So diagnosing overfitting requires inspecting both the training and the validation curve together. Okay. So a good fit is our goal when training machine learning models, as shown by this figure. And it occurs at the sweet spot where the model is neither underfitting nor overfitting. So when we have a good fit, the training and validation losses will both decrease at a large rate of decrease initially, and then get smaller over time until they reach a point of stability, or in other words, they converge. And people also refer to this as reaching a plateau, okay? And ideally, the training and validation loss curve will plateau to similar values, but you will often see a small gap between the two and where the training curve converges to a lower loss value than the validation loss. And this gap between training loss and validation loss is referred to as a generalization gap. And intuitively, we can expect this to happen because the model is directly optimizing to perform well on the training set, right? And now remember, we also mentioned earlier that continuing to train a model that is at a good fit can turn it into an overfit model. And in terms of loss curve, we can think of this as the training loss of our model continuing to go down gradually while the validation loss start to go in the opposite directions and increase. And this is the classic sign of overfitting, okay? And in addition to plotting learning curve of the loss to monitor and debug during the model training process, machine learning practitioners often plot learning curve for other metrics as well. And a common second type of learning curve to visualize during training is the plot of the final performance metric, for example, accuracy. And this is useful to get a sense of actual model performance because lower loss usually correspond to better model performance. But it does not tell us whether the accuracy is at a level we are happy with or not, right? So performance curves, such as accuracy curve, can also provide additional information to complement our analysis when we diagnose issues from learning curve. And now we have seen how to interpret learning curve to monitor the learning process and diagnose problems, including some of the most common problems of overfitting versus underfitting. But we also need to know how to address the problem once we find them, right? For now, we have seen some examples of underfitting and overfitting, but the question is now what we can do to prevent them. So first, let's discuss typical approaches for solving underfitting. Then we will discuss solutions for overfitting, introducing the concept of regularization along the way. So a model underfits when it is unable to learn features from the training set. And this in turn means that it performed poorly on both the training set and the validation set, right? So there are a couple of reasons why this might happen. One could be that our model does not have enough capacity to learn the data that we have, or alternatively, we can say that our model is not able to learn a function that allows it to get the low loss on the training set. So let's say our training set consists of two features shown here. And if this was a regression task and our goal was to match the shape of the data, then we will need to have a model with the capability of forming this shape of the green line, right? But if we use the linear regression model, for example, which can only produce straight lines, then we will never get that good match. And note that this is one of the reasons why neural networks have become so popular. Because of the complexity of interaction between parameters, they are capable of producing any shape or function, okay? So the solution to underfitting are relatively straightforward. So the first thing is to try to train our model for more time. And sometimes what looks like underfitting is a model that just has not had enough time to find the features that are meaningful in the training set. So make sure to check this first before trying other options, okay? But if it looks like we are still underfitting, then we can start trying increasing the capacity of our model, or in other words, the number of parameters and therefore the complexity of the functions we can model, okay? And one way to do that would be to try on neural network, for example, if you are not using this already, since as we saw earlier, neural network in general have many more parameters and it therefore has a higher capacity compared to other types of machine learning approaches. But if you are already using a neural network, then we can consider increasing the number of layers or adding more neurons per layer, which both can add parameters, okay? And now, the solution to overfitting are a little less straightforward. And in fact, it is one of the most active areas of research in machine learning. So the art of reducing overfitting is called regularization. So to regularize a model means to force it to learn and retain general insights that allow it to extrapolate what has learned to unseen data. And here is some examples of a few common regularization techniques. So number one is weight decay. So weight decay or L1 and L2 regularization penalize the model, generally speaking, for using too many or too much of its parameters at its disposal. And this means adding a value in the loss that represent the magnitude of the parameters values or the weight coefficients in the model. So if the model has many non-zero or large weights, then the magnitude will be large as well. If it has few, then the magnitude will be small as well. So since the model is looking to minimize the loss, this constraint forces the model to have small value weights and thus force the model to be less complex. Okay. And a second regularization approach, which is a very common technique in neural network, is dropout. So dropout means randomly setting parameter values to 0 in the model during training. And this means picking a layer of the model that randomly drops out output values and sets them to 0. So the intuition is that that layer will become more unreliable and that the model has to build in redundancy into its subsequent layers. So by having to account for redundancy, the model cannot be as complex. So the probability of dropping out a given neuron is a very common hyperparameter. And next, a third approach for regularization is data augmentation. So data augmentation means randomly transforming the samples in a training set in order to prevent the model from learning any features that are too specific. Okay. So some common augmentations, for example, for images include things like rotating the image, randomly cropping it, resizing the image, adjusting color and brightness, or flipping an image horizontally or vertically. But remember that the reason a model overfits training data or training set is because it gets too familiar with those samples. So by constantly changing what the samples in the training data set look like, we slow down or potentially prevent the model from memorizing that training set. Okay. But one word of warning here, we should be very careful in the transformation that we apply. Because remember that the sample must still reflect the label that they are affiliated with and be realistic for the actual environment they'll be using it for in practice. Okay. So I mentioned about the loss function previously, but that is used for model optimization to identify if a model suffers from underfitting or overfitting. Now we are going to need statistical testing to help us answer the question, does the model perform in a way that allows for useful actions to be taken medically? So now that we have trained machine learning models in minimizing loss, and we have seen that learning hold true on a test set, and we now need to figure out some meaningful metrics to evaluate the performance of our new models with statistics. Okay. So first, let's discuss some key evaluation metrics for classification algorithms. And these are some of the examples. So first of all, I believe for most people, the first metric they will think about how to determine how well a model fits the data set is accuracy. But as a reminder, there are some shortcomings of accuracy as a metric, but let's first start by looking at accuracy. So when computing the accuracy on a test set, we look at the proportion of the total examples that the model correctly classified. Okay. So let's work with an example so we can illustrate the computation of accuracy. So here we have a test set of 10 examples, and 8 of them have the ground truth of normal, and 2 have the ground truth of disease. Okay. And let's say we have a model 1, which outputs negative for all the 10 patients. So a negative here means the model is outputting the prediction of normal. Okay. And this is, of course, it's not a useful model, but notice that it is getting all the normal examples right. So it is getting 8 out of 10 examples right, and thus has an accuracy of 0.8. So let's compare that to model 2. So model 2 correctly predicts positive on the 2 disease examples here, and also calls two of the normal examples positive here and here. Okay, and now we can compute the accuracy of model 2. And if we go through this computation, we'll find once again that we get 8 out of 10 examples right, with model 2 gets an accuracy of 0.8 as well. So we have two models with an accuracy of 0.8. Although we have not formalized this, we get a sense that model 2 is perhaps doing something more useful than model 1, because it is at least attempting to distinguish between healthy and diseased patients, right? So let's understand the accuracy metric a little more. So we will see how we can use the accuracy to derive other useful evaluation metrics such as sensitivity and specificity. And we'll start by interpreting accuracy as the probability of being correct. Okay. And we can break down this probability of being correct as the sum of these two probabilities. So the probability that the model is correct and a patient has the disease, plus the probability that the model is correct and the patient is normal. Okay. And the law of conditional probability allows us to further expand this out. And as a reminder, the law of conditional probability says that the probability of A and B is the probability of A given B times the probability of B. Okay. And we can apply this to the first term to expand this to expand it out here, and to the second term as well to expand it out here. Okay. And what this allows us to do is to interpret these terms over here. The probability of being correct given the patient has the disease means that we predicted positive, right? So we can replace this by the probability that we predict positive given a patient has disease. And similarly, the probability of being correct when the patient is normal would mean that we predicted negative. So we can replace this by the probability of predicting negative given a normal patient. Okay. So out of this expression, pop out two very important quantities that are probably the bread and butter of evaluation in medicine. That is sensitivity and specificity. Okay. And these terms are also known by true positive rate and true negative rate, which refer to the same two quantities. Okay. So sensitivity is a probability that the model classifies a patient as having the disease given that they have the disease. Okay. And whereas specificity is the probability that the model classifies a patient of being normal given that they are normal. Okay. And thus, we have broken our global measure of accuracy down into the two useful quantities of sensitivity and specificity. Okay. And the other piece of useful terminology is for the remaining terms over here. The probability of a patient having disease in a population is called the prevalence. And the probability of being normal is simply 1 minus the prevalence. We can thus write accuracy in terms of sensitivity, specificity, and prevalence, right? So why is this useful? So this equation allows us to see accuracy as a weighted average of sensitivity and specificity. And the weight is associated, with the sensitivity is the prevalence, while the weight associated with specificity is 1 minus the prevalence. And this equation also allows us to find out any of these quantities given the other three quantities, right? So let's see using this as an example. So first we compute the sensitivity. So sensitivity can be computed as the fraction of disease examples that are also positive. So in the denominator, we have the number of disease examples, which is 1, 2, and 3, right? And in the numerator, the number of positive and disease examples. So this is going to be 1 and 2, right? So we have 2 out of 3 or 0.67, okay? And then we compute specificity. So specificity can be computed as the fraction of normal examples that are also negative. So in the denominator, we have the number of normal examples, which is going to be 7. And in the numerator, the number of negative and normal examples. So this is going to be 1, 2, 3, 4, 5, and 6. Okay. So this is 6 over 7 to get 0.86. So that's the computation of sensitivity and specificity. Okay. And now let's look at the prevalence of disease in this set. So this is simply the fraction of disease examples computed as the number of disease examples over the total number of examples, which is 3 out of 10 or 0.3. And now using the relationship between sensitivity, specificity, and prevalence, we can also get to the accuracy, right? So this is going to be equal to 0.67 times the prevalence, 0.3, and plus the specificity, 0.86 times 1 minus prevalence, or 1 minus 0.3, so 0.7. And this comes out to be 0.8. And we can confirm with a simple calculation of the fraction that we get correct that the accuracy is indeed 0.8. So we have covered 2 metrics we can use to evaluate diagnostic AI models, including sensitivity and specificity. And we have seen how they are related to accuracy, right? So sensitivity tells us, given we know a patient has a disease, what is the probability that the model predicts positive? But in the clinic, the doctor using an AI model may be interested in a different question, because in most cases, the doctor does not know whether the patient has the disease or not, right? But they do know what is the output of the AI model, right? And that is given the model predicts positive on a patient, what is the probability that they actually have the disease? So this is called the positive predictive value or PPV of the model, okay? And similarly, while specificity asks what is the probability the model predicts negative given a patient is normal, the doctor might be interested in knowing that the probability that the patient is normal given the model prediction is negative. So this is called the negative predictive value or NPV of a model, okay? So let's compute the PPV and NPV on this example. So once again, we have 10 examples on which a model has made its predictions. And first, let's compute the PPV. So PPV can be computed as the fraction of positive examples that are also diseased. So in the denominator, we will have the number of positive, which is 1, 2, 3, and 4, right? So in the numerator, the number of positive and disease. So there is 1 and there is 2. So we have only 2, and then we get a PPV of 2 over 4, which is 0.5, right? And let's now look at the NPV. So NPV can be computed as the fraction of negative examples that are also normal. So in the denominator, we are looking at everywhere the model prediction is negative, which is 1, 2, 3, 4, 5, and 6, right? And in the numerator, all the places where it is negative and the ground truth is normal. So there is 1, 2, 3, 4, and 5, right? So this is 5 over 6 or 0.83. Okay, oh, sorry. And now that we have seen PPV and NPV in addition to sensitivity and specificity. So now let's look at how they relate to each other, okay? So to see their relation, we'll use the confusion matrix. So the confusion matrix can be used to look at the performance of a classifier in the form of table. So the rows correspond to the ground truth and the columns to the model predictions or the model outputs, okay? And the cells in the tables correspond to the number of elements to corresponding to each ground truth model predictions combination. So for example, in this cell, we will have the counts where we have a ground truth of disease and at the same time, the model output of positive, okay? And see, we have this and this in this example. So that is two examples, right? And the sum of these four cells should be the total number of examples, okay? Which is in this case is 10, okay? And these four counts are more generally known as true positive, true negative, false positive, and false negative, okay? So a true positive is an outcome where the model correctly predicts the positive class. And similarly, for true negative, it is an outcome where the model correctly predicts the negative class. And a false positive is an outcome where the model incorrectly predicts the positive class. And a false negative is an outcome where the model incorrectly predicts the negative class, okay? So we have seen the formulas for the computation of each of these metrics in terms of counts, and note that they directly correspond to cells in the confusion matrix. So for instance, for PPV, we deal with the count here of the top left cell divided by, in the denominator, this column over here. That gives the total number of examples where a positive prediction was made, okay? And another metric, specificity, is looking here at the number of negative and normal, which correspond to the bottom right cell here. And in the denominator, to the total in the bottom row here. Thus, looking at all of the examples where the ground truth is normal, okay? So we can represent all of these metrics in terms of these four terms. So here is the transformation of the formulas to use the terms in the confusion matrix. So for example, PPV is now true positive divided by true positive plus false positive, okay? And thus, the confusion matrix can be used to derive all of these four metrics that we have looked at to evaluate the performance of a model, okay? And other metrics, which is quite commonly used in machine learning, are precision, recall, and F1 score. So precision is the same as PPV and computed using the same equation. And on the other hand, recall is the same as sensitivity and computed using the same equation as well. And lastly, F1 measure is a function of precision and recall. And it is needed when we want to seek a balance between precision and recall. So we have mentioned accuracy. So what is the difference between F1 score and accuracy then? So we have previously seen that accuracy can be largely contributed by a large number of true negative, which commonly seen in healthcare. So in this case, F1 score might be a better measure to use if there is an uneven cost distribution, okay? And lastly, we look at one of the most useful tools to evaluate medical AI models, the receiver operating characteristic, or ROC curve. And we will see how the ROC curve allows us to visually plot the sensitivity of a model against the specificity of the model at different decision thresholds. So for example, we have a chest X-ray classification model that outputs a probability of disease given an X-ray, okay? And this output can be transformed into a diagnosis using a threshold or what we call operating point. So when the probability is above a threshold, then we interpret this as positive or saying the patient has the disease, okay? But when the probability is below the threshold, then we interpret this as negative or saying that the patient does not have the disease, okay? So for example, if our probability score is 0.7 and our threshold we set at 0.5, then we will classify this example as positive. But if our probability score was 0.2 and our threshold was still 0.5, then we will classify this example as negative, okay? So our choice of threshold affects the metrics we have looked at so far. So for example, if we had a threshold of t of 0, then we will classify everything as positive, right? And so our sensitivity in this case will be 1, while our specificity will be 0. And similarly, if we had chosen a threshold of 1, then it means that we will classify everything as negative. So our specificity will be 1, while our sensitivity will be 0. Okay, so let's dive further into how our choice of threshold, also called the operating point, affects these quantities. So let's say we have a test set of 15 chest x-rays, which we ran through our model to get an output probability or a score for each of them. And we can plot these 15 output scores on a number line between 0 and 1. And now some of these x-rays will have a ground truth of disease and some will be normal. So let's color them accordingly. So here disease is red and normal is blue, okay? So we can pick a threshold, small t, that sets everything on the right-hand side of the threshold as we classify positive, and everything on the left-hand side of the threshold we classify as negative. So now notice that we can compute the sensitivity and specificity of the model, right? And here, the denominator for the sensitivity is the total number of disease example, which we can count as the total number of red, which is going to be 7, right? And the numerator is how many of those are positive, or in other words, on the right-hand side of the threshold. So this is all of them except 1, so which is 6. So our sensitivity now is 6/7, or 0.85, okay? And similarly, the denominator for specificity is the total number of normal examples, right? Which is the total number of blue circles here, which is going to be 8. And the numerator is how many of those are negative, or in other words, on the left-hand side of the threshold, right? And this is all except 2 here and here. So this is 6, okay? So our specificity is 6/8, or 0.75, okay? But now let's say we change the threshold such that it was higher. And we now expect we classify fewer examples as positive and more examples as negative, right? And we can now recompute the sensitivity and specificity. And note that the sensitivity has gone down, our numerator has fallen, and the specificity has gone up because our numerator has increased, because we are now correctly classifying more normal patients and incorrectly classifying more disease patients, right? So we can take this example to the extreme. And so for example, we set the threshold to be at 1. And in this case, sensitivity is going to be 0, since none of the examples are classified positive. And our specificity is going to be 1, since all the examples are classified as negative, right? So if we compute the sensitivity and specificity at every possible threshold, then we can obtain such curve, which is called receiver operating characteristic, or ROC curve, okay? So ROC curve is a wonderful metric for evaluating the model performance considering a range of thresholds at the same time. So now let's look at the ROC curve, which is a plot of sensitivity on the y-axis against the false positive ratio, or 1 minus specificity on the x-axis. And the cool thing about ROC curve is that they give us the ability to assess the performance of the model over its entire possible threshold or operating range. And we can see what happens to our models with our model performance with threshold from 0 all the way to 1 for a given label. So it is pretty great, right? And we often report the results of the ROC curve analysis as the area under the curve AUC, or otherwise known as area under the curve or AORC. Okay, so most people in medicine, in the biomedical sciences, they are pretty familiar with this metric for evaluation of a test. And let's look at a couple scenarios as a reminder. So to compare the performance between two or more classifiers, either performance characteristic at a particular operating points or threshold can be compared, or overall performance can be compared using AUC. But one thing to watch out here, many published reports compare AUCs in absolute terms. So for example, here, classifier 1 has an AUC of 0.79 and classifier 2 has an AUC of 0.58. So classifier 1 is clearly better, but actually this does not necessarily hold. As with any other comparison on estimation with uncertainty, so it is important to perform statistical analysis to confirm if differences are statistically significant. Okay. So now we have discussed some key evaluation metrics for classification algorithms. And next, let's briefly discuss two key evaluation metrics for regression algorithms. Okay. So the first one are mean square error, or MSE, and root mean square error, or RMSE. So MSE is an absolute measure of the goodness for the fit. So MSE is calculated by the sum of square of prediction error, which is the real output minus the predicted output, or y hat, and then divided by the number of data points. Okay, so it gives us an absolute number on how much our predicted results deviate from the actual number. And of course, we cannot interpret much insight from one single result, but it gives us a real number to compare against other model results and to help us select the best regression model. Okay, and in addition, RMSE is the square root of MSE, and it is used more commonly than MSE because firstly, sometimes MSE value can be too big to compare easily, and secondly, MSE is calculated by the square of error, right? And thus square root brings it back to the same level of prediction error and make it easier for interpretation. Okay. So for example, now our model tried to predict the hospital length for 3 patients here. So we can just input the number into the equation, the ground truth y, and the model predictions y hat, and we will obtain the MSE and the RMSE of the model. So pretty straightforward. Okay. So the second one is mean absolute error, or MAE, which is similar to MSE. However, instead of the sum of square of error in MSE, MAE is taking the sum of absolute value of error. So compared to MSE or RMSE, MAE is a more direct representation of sum of error terms, where MSE gives larger penalization to big prediction error by squaring it, while MAE treats all errors the same. Okay. So using the same examples as before, we can get a MAE of 7.67, and in fact, it is less than the RMSE value computed before. And it is, as I said before, the MSE gives larger penalization to big prediction error by squaring it, while MAE treats all errors the same. Okay, so this is about the end of our discussion about evaluation metrics for regression algorithms. So is there any questions so far before we go, before we continue? If not, then probably we can take a short break before continuing. So how about we will be back at 11:35. Is it okay? So yeah, see you again at 11:35. Okay. Okay, so hopefully all of you are back and let's continue. So we will now look briefly at another very important aspect of evaluating medical models, and that is reporting the variability in our estimate. So I want to introduce briefly about the concept of confidence interval. Okay, so let's say there were 50,000 patients in a hospital, and we wanted to find out the accuracy of our chest X-ray models on everyone who gets the chest X-ray in the hospital. And if we were able to run the model and get the ground truth for all patients, then we will be able to get the performance of the model on the whole population, right? So for example, say we are looking at accuracy, but this could be any other metric, okay? And we find that the accuracy of the model around all 50,000 patients is 0.78. So this is called the population accuracy, here with small p, okay? But in reality, we do not want to test the model on the whole population because sometimes it is simply infeasible to do so. And therefore, the population accuracy p is unknown. And the question is, can we get a sense of how well the model will perform on this population by using a small sample of patients? So let's say we sample 100 patients from the hospital. And now we find that the model gets an accuracy of 0.8 on the test set. So can we say anything about the range in which the population accuracy P will lie? So confidence interval allows us to say that using our sample, we are 95% confident that the population accuracy P is in the interval 0.72 and 0.88. So 0.72 here is called the lower bound and 0.88 the upper bound of this interval. And the calculation of these confidence intervals is simply beyond the scope of this workshop, but it is important to understand the interpretation, okay? So when we report the accuracy of a model on the sample, we report it with the mean and the confidence interval. And the 95% confidence interval here allows us to say that with 95% confidence, P is the interval 0.72 and 0.88. And what we have not seen is what it means to be 95% confident. So 95% confidence does not say that there is a 95% probability that P lies within this interval. And it also does not say that 95% of the sample accuracies lie within this interval. So the interpretation of 95% confidence is a little more nuanced and requires us to think about making repeated samples, okay? So let's dive into this. Let's say we were able to repeatedly sample in 100 patients from the population several times. And each time we get a different sample and hence a different sample accuracy. And we can also compute the confidence interval associated with each sample, okay? And we can look at these samples on a plot. And for each of these samples, we can plot the sample accuracies here represented by the circle and the lower and upper bounds of the confidence intervals of the samples, okay? And on this plot, we also have the true population accuracy plotted as the dotted line. But remember that, that this is unobserved, okay? We don't know. And note that most of the samples contains the population accuracy, this vertical line, right? And here, 6 out of 7 contain it and only 1 misses it, okay? And in fact, when we have 95% confidence interval, 95% of the samples will contain the population accuracy. So 95% is what is called our confidence level. And thus, the interpretation of 95% confidence is that in repeated sampling, this method produces intervals that include the population accuracy in about 95% of the samples, okay? But in practice, we do not compute the confidence intervals for many samples and we only compute our model performance on one sample. And for our sample, the computed confidence interval may or may not contain the P, okay? But we can be 95% confident that it does, okay? And one of the factors that affects the width of the confidence intervals, which is given by how close these numbers are, is the sample size. So let's say we drew another sample from the population, but this time with 500 patients. And this is 5 times as large as our previous sample. And we can expect that we'll have a better estimate of the population accuracy using the larger sample. And we can see that even though the model gets an accuracy of 0.8 on both samples, notice that the confidence intervals are tighter for the larger samples and wider for the smaller sample, right? And thus, a larger sample is giving us better estimate of this population accuracy because these numbers are closer together, okay? And to summarize, confidence intervals are useful because even when we cannot run the model on a whole population, we can at least use a test result on a sample to express the range in which we are pretty sure our population accuracy lies, okay? So now we have finished our discussion about model evaluation. And next, let's discuss about some issues in the application of AI in healthcare, okay? So we have covered a lot of ground of clinical machine learning so far. We should feel like we have a solid understanding of the principles of machine learning, as well as how we build and evaluate them in the laboratory environment. Though we have spent most of the time discussing the upside or potential to improve healthcare with machine learning, it is equally important to recognize that, like all technologies, practical uses of machine learning in healthcare do not come without certain challenges, or as we like to call them, opportunities. So now, as the last topic of our workshop this morning, we will cover some of the important concepts beyond the challenges related to applying AI in healthcare, okay? So now, let's talk about a simple but surprisingly challenging concept behind the technology of machine learning and healthcare: correlation and causation. Because machine learning methods, such as neural networks, simply learn association between the inputs and the outputs to find the best fit, regardless of what features it needs, and they can sometimes be unreliable or even dangerous when used for driving medical decisions. So why is this the case? Well, we have learned that since they are not actually explicitly programmed, machine learning algorithms can and will use whatever signals are available to achieve the best possible performance in the dataset used. So we must recognize that the model or function that is created can, in many instances, come from patterns in the data that are correlations rather than causative truths about the label, or in other words, about the outcome of or the disease, okay? So if a model to fit the data is based on useless correlations due to either coincidence or the presence of unforeseen variables, also referred to in machine learning language as common response variables, confounding variables, or lurking variables, it can be problematic for translation into clinical care. And even though the intention, the hope is that these algorithms will learn the most clinically useful and appropriate model features instead of learning false correlations. And the issue that comes up in machine learning, especially with neural networks, is the situation where the model exploits unexpected or even unknown confounders that have no relevance in the task. And that will severely impair or invalidate the model's ability to generalize to new datasets. And this happens because for the most part, correlation often does work well for machine learning models to accurately classify problems in large data sets and predict outcomes. But without medical context, this can lead to attempts to address the predictors as factors that can be manipulated to change outcomes, who will do nothing at best, but certainly will not lead to the intended goal of using machine learning to improve healthcare, okay? And we have already mentioned the chest X-ray image example, where an AI model recognized the label in the image to make predictions. And even though the model was considered very accurate, it was focusing on non-medical cues in the image to draw the conclusions. And this issue does not come up only in imaging models, but also in models designed with structured EHR data as well. So, for example, there was one group that trained a machine learning model using EHR data to predict the risk of death for pneumonia patients. So the hope was that the model could automatically identify patients at high risk who could be treated more aggressively, and also find those at low risk who could be safely treated at home. And then they built their model using historical EHR data, and it worked really well. But however, they found later that the model focused on a key correlation to make accurate predictions that was problematic. And in this case, they found that the model predicted that pneumonia patients who also had asthma were low risk, suggesting that asthma is somehow a good prognosis for pneumonia. But this sounds wrong, of course, especially for our medical audience. And it should be clear that there is some problem and the data should be re-examined immediately, as the risk for bad pneumonia outcomes for asthma patients should be much higher than for non-asthma patients, right? So was the model wrong? No, was not wrong at all. It actually had created a model that worked perfectly on the data that they used to train the model, and the model had passed all the metrics. But when they looked into it more, they realized the model was trained on historical data from an institution that did have better outcomes for asthma patients. So that was true. But it was true because of a hospital policy for patients who have asthma that was put in place. So for this institution, for asthma patients with pneumonia, they were directly admitted automatically to the intensive care unit, where they receive aggressive treatment by protocol, and which over time improved pneumonia prognosis for patients who also had asthma in this hospital. So the model did not know that there was a policy that helped the pneumonia patients who also had asthma get better. It just found that there was a correlation in the data that pneumonia patients with asthma had better outcomes than if they do not have asthma. And fortunately, the research team noticed this confounded finding, and the model was never used in practice. But imagine that this model was deployed. And in that scenario, pneumonia patients who are at a much higher risk of bad outcomes, in particular patients with asthma, will have been flagged as low risk and possibly given outpatient treatment or sent home instead of being sent to the intensive care unit. So historical and electronic medical record data sets in this case, even though they were properly constructed, properly labeled, and passed all the metrics, led to the creation of a machine learning model that ultimately infer pneumonia outcomes based on trends from hospital policy and not based on real-world physiological risk. And imagine all the work that went into developing these models only to realize that they are not clinically useful. And this is actually a surprisingly common pitfall, despite being an easy concept to grasp. So with this example, we see that the data led to a training of a model focused on correlations that were not necessarily helpful for the desired outcome. But what if I told you that we could actually use a model that relied on clinically inaccurate correlation, just like those examples in a legitimate healthcare application? So how will that be possible? So the best answer for this is to reconfigure the model's application context. So for now, let's consider an example. Say we had 1 year of retrospective data on 1 million people that was labeled with heart attack or no heart attack. And our team decided to use this label data to train a supervised machine learning model to predict heart attack risk within 12 months, okay? And if we plan to use this model in the clinical setting as a medically accurate model, then it will be important to ensure that the training data had features associated with heart attack risk, such as age, race, gender, lipid levels, and blood pressure. And this will help ensure a causal model that consider underlying biological roles and mechanisms that led to heart attacks. But what if we train a model that ended up focusing on correlations in the data? So for example, it was very accurate, but when we did some investigation, it turned out that the model was using gray hair color as a predictor for a heart attack. So is it totally useless? So actually, it depends on the application context. So if our application context was not for treating patients in a clinic, but instead as a model applied for financial or population health or medical practice management, we could actually be pretty okay if we build an accurate model based on only correlative features in our prediction model. So how is that possible? So suppose you are a CEO of a managed care organization, you will allow the model to choose every possible variable available, even hair color, to predict the heart attack risk. And the resulting model will most likely learn to weight these correlation features like hair color as an important factor for heart attack risk, predicting that people with white or gray hair have a higher risk of heart attack in the next 12 months. And now, clearly, that this is not a medically relevant correlation, and coloring gray people's hair to black as an intervention will not reduce the heart attack risk, right? However, if one needs to estimate financial risk in ensuring the 1 million individuals and a large fraction of that population has white or gray hair, then a model need not be causal or need to be useful for a case like financial risk planning in large medical organization, okay? So why does it sometimes seem that even supervised machine learning models are so prone to solving the wrong problem? So, well, for one, they, by design, develop their own ways of solving a problem rather than relying on step-by-step instructions from our programmer. And remember that we discussed that in the initial introduction. And secondly, most importantly, they have no contextual knowledge to understand the context of the possible solutions. And remember that there is no common sense without context. And it is important to emphasize that even or especially when a healthcare model seems to be working well by all the metrics and benchmark we discussed in the prior model, we still need to carefully consider and dissect the possible spurious correlations to prevent patient harm. And this is the reason why multidisciplinary teams with domain experts are absolutely critical to machine learning in healthcare model development, evaluation, and deployment, okay? And the issues with correlations that we talk about in datasets that can be learned by algorithms are at the core of the ongoing tensions in machine learning and healthcare that exists between what you will hear referred to as black box versus interpretable model algorithms. So many machine learning models for healthcare applications have been shown to be capable of reliably detecting atrial fibrillation from electrocardiography, retinopathy from optical coherence tomography, and in-hospital mortality risk from electronic health records. And even more abstract clinical situations, such as predicting the onset of sepsis before clinician recognition. So the machine learning models that have achieved this high performance are based mainly on deep learning and rely on vast amounts of data and complex model structures with millions of parameters. So for example, the Inception V3 model from Google, which is more accurate than physicians at identifying diabetic retinopathy from fundus photographs, has 23 million parameters. So this complexity can make it difficult to understand exactly how these models make a given decision or prediction and have earned them the name black boxes. And in contrast, models with fewer features are easier to visualize, understand, and explain, as we have seen with regression or decision trees, for example. So there is this trade-off that exists. To improve interpretability often means reducing the number of predictive variables, but that may lead to a reduction in the performance of the model, okay? And we can expect that deep neural networks will be the least explainable, whereas linear regression and decision trees will remain the most explainable. Because deep neural networks have been so high performing, yet exhibit this weakness in terms of interpretability. So there are many ongoing efforts to try to bring more interpretability to these neural networks, So some strategies include leveraging multidisciplinary teams to review false positive and false negative cases predicted by the model, and testing the model on external datasets to try to gain insight into causal versus correlative features learned by the model. And other strategies also focus on developing computational methods to interpret neural network predictions. Okay. And at this point, I also want to mention one terminology thing, which is that you will often hear various words being used that are related to the concept of interpretability, such as transparency, explainability, and inspectability. And these terms mean essentially what they sound like. So a model that is transparent should allow us to easily understand how it works, okay? And a model that is explainable should be able to easily communicate why any particular output is produced, okay? And a model that is inspectable should allow us to probe and inspect the functioning of any part of the model, okay? So the terms are often used in overlapping and overloaded ways, and many people use them more generally to get at the overarching idea of model interpretability. So in other words, they're always to get at the notion of opening up the black box of complex models, such as deep neural networks. So let's talk a little bit about more specifically about what's the deal with the black box anyways. So it has become quite common these days to hear people refer to machine learning systems as black boxes, okay? So the black box metaphor refers to a system for which we can only observe the inputs and the outputs, but not for the internal workings. And for as long as there has been a machine learning field, there has been discussions and debates on the topic of interpretability and referential metaphors about the black box. And in healthcare, there remains concern about black box models, even if they have been properly vetted and can reliably achieve high performance. After all, we have seen with some of the examples earlier how badly things can go wrong when models are in spurious correlations in the data. But even when we can properly vet a model to ensure that these spurious correlations do not exist, it is unclear whether complete explainability is actually necessary. So as Geoff Hinton, a leader in AI, was quoted on the subject, clinicians and regulators should not insist on explainability because people cannot explain how they work for most of the things they do. So increasing model transparency can also have the opposite effect and may contribute to the dangerous levels of trust in the model. And it can lead to overconfidence or over-reliance on the model and human error. And after all, many clinicians will also tell you that sometimes they do not always know how or why they arrive at a particular diagnosis. And further, many common medications like aspirin and penicillin were used for decades in patients, long before medical science understood how they work. So when we think about the black box and model transparency, the question is whether it makes sense to hold AI models to a higher standard of interpretability than routine clinical practice. And however we land in response to this question, there is still a lot of work in the area of model interpretability and answer to the question of unlocking the black box. So the first step towards answering this question is consider it as two distinct flavors of machine learning model explainability, intrinsic and post hoc explainability. So intrinsic interpretability is simply referring to models, often simple models, that are self-explanatory from the start. Whereas in contrast to intrinsic interpretability is post hoc interpretability, which is used to understand decisions by complex models that do not have prescriptive declarative knowledge representations or features. So let's consider an example of intrinsic interpretability and why in healthcare it would be deemed an advantage. So for example, the LACE index, it predicts 30-day hospital readmission risk and is calculated using the following 4 intuitive and transparent feature inputs: length of current admissions, admission acuity, patient comorbidities, and the number of emergency departments visits in the last 6 months. So when interpreting the LACE index, clinicians can use their own clinical judgment because they know what the features are, and they can adjust the estimate of a patient's readmission risk if they have additional information about one of the features that the model is considering, or has other information about features that the model does not consider. So let's consider a patient with dementia who is otherwise healthy but experience an extended hospital admission because of a prolonged guardianship process. And based on this scenario, the length of stay by the LACE index model will likely predict a higher risk for readmission. But because the clinicians can modify the assessment, knowing that the lengthy admission was not due to clinical factors, to avoid unneeded additional intervention. And this is only possible because the risk factors are known to the clinician and interpretable in the setting of clinical judgment and routine care. Okay. Now, if we contrast that with more complex machine learning models that, as we have seen, consider multitudes more features than previous example risk or model. And it is practically impossible to apply intrinsic interoperability and physician judgment, right? Instead, we consider a post hoc interpretability on a case-by-case basis, which can be more challenging. So imagine if the LACE score was instead a black box that considered thousands of features instead of just 4. And then clinicians will instead need to review a post hoc explanation of the model's predictions before a similar judgment could be made. And in sometimes that can be impossible because they have to consider an approximation of both thousands or even millions of potential features. But then they also have to consider the interaction between those features that complex machine learning models depend on for classification or prediction. And in that case, it will be way harder to adjust the use of the model with clinical judgment because it will not be possible to know which feature contributed to the recommendation in the same way as with intrinsic interpretability models like the original LACE score we discussed. Okay. So, well, it may be true that many clinicians are more comfortable with models that have predictions which are easily understood, but it becomes a challenge when they start using black box model that may be more accurate because they use many different features, but it causes them to have a difficult choice of performance over interpretability, right? And this end up being mainly about trust. So you have to trust in the development methods, the data, the metrics, as well as the outcomes data of using the model if that is known. And this is why rigorous testing is so critical in clinical machine learning. And having an understanding of the applications during development and adjusting the metrics accordingly is very important. Okay, so this is about the end of our morning session. Is there any questions? If not, then we can go for a lunch break and we will see you again in the afternoon at 1:30 p.m. For the hands-on lab session. Okay. And feel free to ask in the chat box if you have any questions in between. Okay. So see you all again in the afternoon.